All right, extension problems, applications. We have a village of 7,000 people, and Carolyn comes back from her vacation and has a highly contagious stomach virus. So she's going to get everybody sick, or she's going to get a lot of people sick. So we're going to evaluate how that's going to work. The first thing we're going to do using this equation is see how many people she's going to get sick after 4 days. So what we're going to do is we're going to take our equation, that's 7,000 over 1 plus 6,999 e to the negative 0.7t, and our t is 4, and put that in our calculator. If you're doing this extension work and you don't know how to put that in your calculator as a fancy fraction, a stacked fraction like that, please let me know. I can help you and it will make your life easier. And when you put that in your calculator, you should get 16.408. So we have approximately 16 people have this highly contagious stomach virus after 4 days. So it says that the government will evacuate the village when 30% or more of the villagers are infected. So what we need to do before we figure out how many days that's going to take is figure out what 30% of 7,000 is. So our first step here for part B is do 30% of 7,000. And that gives us 2,100. So when 2,100 people are sick, we're going to evacuate. So in order to do our problem here, after how many days, we're going to set our equation equal to 2,100. It's a lot of writing. I feel like these problems are more writing than they are really algebra, although there's lots of algebra to do as well. So we need to move that denominator over by multiplication. Moving that by multiplication lets us get it out of the denominator, which is what we want. We don't want to work with fractions here. We've got enough going on as it is. So, doing that multiply step lets us get that mess out of our denominator and keep rolling. So over on the left side of our equation, we have 2,100 times that denominator, that old denominator. You could multiply that 2,100 through. I think it would be more steps for you. I think it's going to be easier to just divide both sides by 2,100. Go ahead and reduce your fraction. Again, if this is the problem that you're choosing to tackle on the test, you will be given a calculator for this portion. I'm still going to do this subtraction. One is really common denominator, a really easy common denominator to create here. I'm going to subtract 21 over 21 is the same as subtracting 1. 70 minus 21 is 49 over 21. just a couple more steps. We're so close. Hang in there. We're going to divide both sides by 6,999. I went ahead and put that in my calculator, although you wouldn't need to. Actually, I didn't put that in my calculator. I'm sorry, I misspoke. I took the ln of both sides. So at this point, I went ahead and took the ln, and that lets me pull down that exponent. And I took the ln of the other side too. Don't forget to do that. Your calculator can handle 49 over 21 divided by 6,999. And you can let it. That's actually a lovely thing to do because then you're doing less rounding. The less you round, the more exact your answer is going to be. ln of e is 1, so that guy goes away. Negative 0.7 is what we're going to divide by. So your graphing calculator can absolutely handle that mess over there on the right side of the equation. And again, the less times you round, the better. When I put that in my calculator, I got 11.437. This is a super nasty stomach virus that showed up back from the Galapagos Islands. And in 11 days, they're going to evacuate the town to make sure that nobody else gets sick. All right, number 21 is another of the extension problems. It's this other logistic growth problem. The probability that you share a birthday with someone can be modeled by a logistic growth equation. And it's actually the probability that you share a birthday with someone that's in the same room as you are is really high. So this model, it says, when is it going to fall below 10%? I'm sorry, I misspoke. That no two people share a birthday. The probability that you do share a birthday is high. The probability that you don't is going to be low. This equation models the probability of no two people sharing a birthday. Sorry. I'm sorry that I misspoke. So what we're doing with this